Hi everyone, I am Deepak from Tata Institute of Fundamental Research, Hyderabad. Today I will discuss one particular problem that I am working from last 4 years in my PhD. The title of my talk is MOS2 as a next generation transistor. Electronics devices are everywhere around us, from mobile phone, laptop to desktop. Inside all these devices, there is an important component called IC, which is consist of million of transistors, capacitors and resistors. Transistors are the most important component in an IC, and the number of transistors is directly proportional to the memory or the RAM of the devices. So to increase the memory of the devices, we need to increase the number of transistor per unit volume, that is transistor density. At 1985, an engineer cum physicist, Professor Murray, predicted that in every 2 years, the number of transistors in a silicon chip have to be doubled, called Murray's law. So you can see from the graph that the number of transistors increase linearly with time by making the size of the transistor smaller and smaller. As you can see from the graph that below 5 nanometer, the linear graph started deviating. That indicates that we reached its maximum limit, because below 3 nanometer, silicon itself is not thermally stable. So what next? How we can increase the memory of the device further? So we need to think beyond silicon. Research predicts that the MOS2, being a two-dimensional material, can be a possible replacement of silicon due to its atomic level thickness, reduced dielectric scaling, and 2D quantum confinement effect. Recently, Professor Andesky's group demonstrated MOS2 as a fast 2D semiconductor over 1000 transistor for practical application, replacing silicon by MOS2. Although you can increase the transistor density of the whole device, still the individual performance of a MOS2 transistor is poor. As you can see from the figure, the on-off ratio of the MOS2 transistor is found to be 10 to the power 3, whereas the silicon transistor, it is 10 to the power 7 to 10 to the power 8. So we need to increase the individual transistor performance. The low performance of a MOS2 transistor can be due to defects and grain boundaries present in the material and the contact resistance in the metal semiconductor interface. So in our lab, we grew large area monolayer MOS2 sample using chemical vapor deposition technique. We have performed various characterization techniques such as Raman, AFM, XPS, SEM to establish the high quality of the sample. Then we demonstrated their device performance in transistor application, which shows an extraordinary on-off ratio around 10 to the power 7. We also developed an approach to minimize the contact resistance issues by interface modification approach, which result in significant enhancement in device performance. So in conclusion, I have grown high quality wafer scale monolayer MOS2 and demonstrate their device performances for next generation transistor application. For more details, please visit to my Google Scholar account. Thank you.